Okay, now connecting the last dot of the value chain, it's really wonderful to have the demand side represented at our bifacial event with Tomaso Charlemont, global solar procurement leader at RES. He has 3 decades of experience in commercial development and strategy definition on international scale across the EMA region. Tomaso has strong knowledge of PV inverters and BOs acquired during the past 10 years of activity with the leading players in this field. Tomaso will share his experience with bifacial technology for the development side, from the developer side, sorry. Tomaso, the floor is yours.
Thank you, Shahram. It's a pleasure joining the team. First time for us, actually. Do you hear me okay?
Crystal and clear.
Okay, perfect. So let me start sharing my screen and we can start diving into my presentation. Just tell me when you see the presentation coming up.
Yeah.
It may take. Okay, perfect. All right. So as Shahram introduced, I'm the global solar procurement leader at RES. I will make a brief introduction about who we are and then go straight into RES bifacial project experience and then the impacts that the bifacial has on utility scale project. But just for you to make you acquainted with RES. RES is an acronym that stands for Renewable Energy Systems. We are a private company owned by a British family, the McAlpine family. The family itself has been in the construction business for 150 years, largest construction firm in the UK. RES was founded 40 years ago by the McAlpine family, and over these past 4 decades, we have established a portfolio of over 19 gigawatts of solar and wind projects. So we have 7 gigawatts of projects that we have under asset management and operation maintenance. We are 3,000 people in the organization, which is quite consistent for from a family-owned business, and our activities are developing, building and operating plants. We do not sell energy. We're not a utility. We're not an IPP. So we are a developer with additional services. And we do this across typically 4 technologies, wind, solar, storage, and T&D, transmission distribution. And as you can see from the geography, the countries where we operate are mostly Commonwealth countries because we are a British family owned. So apart from Great Britain, of course, we are present in Canada, the USA, and Australia, and we have a consistent presence in Europe with operations in France, Germany, Sweden, Norway, and also in Turkey. Just a quick look at our history. As I said, we were founded 40 years ago, and that started with basically performing research in the wind technology. And then a few years later, we started building UK's second utility scale wind farm in Cornwall. A few years later, we started building much larger projects. So in 2001, we built the one at that time the largest wind farm in Texas in the US that was at almost 280 megawatt King Mountain wind project. And then a few years later again, we started moving into energy storage. So already in 2014, we had our energy storage project getting operational in also in the US. But before that, we did some solar business already in 2010. We had our first 5 megawatt project developed, constructed, and operated in France. and then we added a T&D business a few years later, and that was a milestone for us to have a 345-kilometer line. That was our first big project connecting USA and Canada that was built by RES. And then we started expanding our activities and started moving into the PPA business. And already a couple of years ago, we started closing our first 1.5 gigawatt of corporate PPAs. So we're definitely leveraging on our vast experience. Now, more closer to the subject of our today's conference is Bifacial. And actually, last year in 2020, RES has completed and brought to commercial operation America's largest bifacial solar project, which is Thousand Oak in Georgia, which is a 216 megawatt peak, 160 megawatt AC project that we already started working on a couple of years earlier. That is in a nutshell to who we are, what we do. Our vision is quite simple. I think will be shared by the most of the audience here today. Is we believe in creating a future where everyone has access to affordable zero carbon energy. That is our vision. Now straight into bifacial, because that's our subject and time goes by very quickly. As I said, our first experience with bifacial started in 2018. That's when we started our engineering work on this beautiful project you see a picture of here. It's in Georgia. And we started engineering 2018. We started construction in the first quarter of 2019, and the project entered commercial operation in Q2 of 2020. Just to give an understanding of what a project of this scale looks like, let me play a brief video that I think will be quite self-explanatory. So I hope you like this video. I've seen it several times, and I cannot get enough of this. It's just impressive. Just for you to get an understanding of what happened since. That was our very first project, and we completed that last year, as I said. But that has been basically the first of a long series. Today, our current bifacial project portfolio exceeds 2 gigawatts, and you have here a list of projects, bifacial projects that we have in our pipeline. As you can see, majority of the projects are in the USA. That is also one of our largest markets, but definitely we see bifacial coming up in France. We have a first 10 megawatt project that we are going to build later this year and finish then beginning of next year. We have a project, a nice project in Canada. Bifacial is getting traction in Canada as well. and then of course Australia, and then further out we also envisage projects in Turkey. That is all related to the public YEKA tender, which is coming up next month. But if we take out the long-term projects that we may have in Turkey, you see that a majority of these 2 gigawatts will happen basically between now and I would say the coming couple of years. So that is the rhythm that we work on. So said that, I think I would like to stop a moment on RES America's, what we call the dual bifacial project experience. And that basically is also what has helped us to gain speed and adopt the bifacial quite quickly, because in North America, we do have something quite unique. We do have basically a dual activity. We both are developers, so that's our development business, where we develop projects from, greenfield projects. We have over 460 megawatts in operation. We have a 2 gigawatt pipeline per year approximately. Today we have a 1.3 gigawatt of pipeline for COD in 2023, typically Texas, Midwest, Southeast US and Canada, because there's one project in Canada as well. But in the USA, we also have a construction business. So we do engineering, construction, procurement, so we are full EPC. So we do ourselves all the bifacial engineering construction, which has led to a lot of experience. We do build our own projects, so RES developed projects, as well as we build for third-party developers, IPPs and utilities. The project that you have seen the video of is a project that we have built for one of our clients that was not developed by RES, but we do self-perform, and we have internal turnkey construction execution teams. So we do everything from grading, pile driving, building the trackers, doing all the foundations, all the civil works, electrical works, everything we do ourselves. And that goes basically today, allows us to have a design and engineering phase, 1.5 gigawatt of projects, and we are over 0.5 gigawatt of projects in construction phase, which are actually building right now. And again, locations typically are the hot solar regions in the US, Texas, Midwest, and Southeast of the USA. Now, what that is, why is that important? Why am I focusing on this? Because the bifacial project impact actually come out of all the lessons learned and solar industry practices for utility scale design, construction, and testing are impacted by the integration of bifacial technology. And that is where we have so much lessons learned. And you will see there's lessons learned, I would say, typically on both sides, on the development side as well on the construction side. And that is what I will be focusing on today. In terms of engineering, what you typically would see is, yes, there is impacts, and that is what, all manufacturers, modules, and trackers especially focus on. That is, yes, with bifacial, you have some basic assumptions which allow you to decrease system size, decrease DC-AC ratio size, decrease your GCR, you improve your yield per area. And then you do, of course, there's an impact on the DC architecture, cable protection devices, etc. So I think there's a few fundamentals that a lot of people are aware of, is that, for the same amount of power, it's just, less surface. So you have a decreased system size. You change your GCR because that is basically the impact of using bifacial. So you can you use lower GCRs. You can play with the heights above the ground of the plane of array that definitely studies have shown can play a role in optimizing the gain. And then you have all your energy yield assumptions, which are based on albedo, module transparency, rear side shading, rear side mismatch, bifacial factor, and so forth. So that is quite, I would say, common knowledge. What becomes a little bit more interesting is on the construction side. The impact on construction is, well, there's a learning curve, and we've been through this. And the impacts of bifacial is, well, it impacts your DC wire management. It does impact labor and installation rates, and not necessarily for the positive. So we will have a closer look at that. And one very, very important point is performance testing and commissioning that gets heavily impacted by bifacial solutions. So I think that is very important to get this understanding of what does it really mean when you install bifacial, when you really make it become real and move out of the numbers. So there's a couple of considerations regarding the engineering part, the project development part, where we basically throw numbers. And so implementing projects, US project on an albedo between 18 and 20% range in regions without snow. I think that's important because snow, when we talk about Canada and other regions where we have snow, then of course you can imagine that albedo is it can be boosted heavily if there's snow on the ground. But nevertheless, let's consider a regular project with an albedo between 18 and 20%. The decrease in overall system size on a DC is anything between 3 and 7% for the same AC system, because that's basically corresponds to the gain that you get from the backside, right, from the rear side. So that's your additional gain, allows you to reduce the DC system, your peak DC system. You decrease GCR depending on land constraints, but that can range between 28 and 33%. So there is really very much depending on the land. Why? Well, because then the land impacts the albedo. So albedo and then modeling, bifacial modeling can bring you this 3 to 7%, which you have basically then up here again. So you basically say, yes, there is a definite impact, positive impact that allowed you to decrease system cost, or say LCOE, as we like to call it. One point that we have realized quite quickly is that the assumption for raising the plane of array, so making basically the torque tube slightly higher to get better irradiation from the rear side, actually with the current pile foundation cost, material and install cost, it is just cost prohibitive. So we will not be able to increase pile heights to increase bifacial gain. It is just not economical. But these numbers is all the calculations that we can do, I typically like to say, on paper, right? Now, interesting enough, you would say, okay, well, that's relatively easy. I would say yes, but keep in mind, and there's a first warning here, that keep in mind that bifacial bears considerably higher amount of variables compared to monofacial, and these variables, they all influence energy production. Now, when we talk about variables, there's a better side and a not so nice side of these numbers. That is basically how credible are these numbers. Well, once you develop a project and you make your yield assumptions, your yield calculation, before you find an investor prepared to put money into your project or take it to a bank, you need to get an independent engineer to validate your assumptions. Well, guess what? The independent engineers, they don't want to take the risk. So these variables that you have here, and you have the list here, they will not take the risk. So what an independent engineer would rather do, they will probably amputate the yield estimate. So they will basically say, well, you think you can produce 100. Well, I only give you 98, and they take 2% out of your yield estimate. So yield estimates, that is the very first point where our learning curve is they must be thorough and well documented. And when I say thorough and well documented, thorough, you have to be precise in what you do, very precise. There's no room for improvisation. But then when I say well documented, albedo value measurements. And again, this is experience talking. Albedo, we have developed a project, and we have taken the albedo based on charts, on widely available charts. I don't remember which source we used, and we have not run our own measuring campaign at the very specific project site. So we have taken charts. That has cost us 3% albedo that was just taken off with a red pen by the IE, because that albedo was not documented. So albedo measurement can be very, very key. And there you see, that you already start, saying, oh, you can do a lot of good work, but it can be just a part of your work just be taken off with a red pen from the independent engineer because you cannot document it. PV module lab test reports and pen files, very, very important. When you present, when you make your yield estimates and you present them to the independent engineer, they would want to see exactly what is the source for the data, or so the pen file that you have been using. So very important, you need to have third-party laboratory validated pen files, and you can get those only if the module manufacturer does extensive testing with an independent laboratory. In North America, typically they would expect a PVEL or RATC. In other regions, it can be TÜV, PI Berlin, etc. So very important, make sure that you have third-party validated test reports, test data. Now, why do we insist on this? Because bifacial, especially now that we see these newer modules coming up with the M10 and G12 cells, etc. Well, it takes time for manufacturers to get through those to the test reports. There are LEETID, LEID reports which require modules to be in a test chamber for weeks and weeks and weeks. The waiting list is getting longer. Sometimes it can take it to a module manufacturer up to 1 year before they have access to the data. So what do? Do you work with preliminary data? Do you work with the manufacturer's data? IEs don't like that. Very careful. That can be quite surprising if you don't prove, or if you cannot prove the validity of the pen file. Your yield will be cut. Tracker documentation. This is something quite interesting. We came through this recently. We are working on a project. We have this tracker, of course, for confidentiality reason, I will not mention the name. We're doing all this work. We presented the yield estimates to the independent engineer. And just because the independent engineer says, I am not familiar with this tracker, I do not know the track record, therefore I will take off 1% of your yield, just because he is not familiar with the tracker manufacturer. That is massive. That is massive. 1% of your entire yield is gone because of the IE. So of course, then you can always build a case. You can always procure documents, etc. But it's running against you. Time goes by, and things like this. It just tells me, make sure that it is very well documented. Then of course, all the PV assist assumptions, which are those who generated the yield, it has to be consistent. So also already from the engineering, it is it is not that simple. You have to do a very thorough work. Then when you go to the other part, it gets actually even more interesting. Unfortunately, time is going by very fast, so I will need to ask the organizers to give me a few more minutes. But when you go to the construction part, balance of system, labor, risk, etc., a lot gets impacted by bifacial. Why? Well, basically because there's a limited industry experience. We built the largest bifacial project in North North America, started construction in 2019. And we went through this, and we are acquiring experience. So, of course, as we move forward, things will improve. But in this initial phase, there are a few things which I thought would be interesting to share. And why is this important? Well, because keep in mind that, and this again is relative to the US market, schedules are quite quick. You know, the project have to move quickly. So going from a contract into engineering, into commercial operation date, you have very, very straight forward dates. And the critical date is what we call the substantial completion date. And then that by that date, that means that commissioning and performance testing must be completed. If you skip that date, you start facing liquidated damages, and they range for anything between $15,000 and $200,000 per day. So depending, of course, on the size and the value of the project, but you cannot allow the luxury for delays. Now, in order to declare substantial completion, that's what you have to do is, you know, to pass performance test. And now performance test liquidated damages, which is basically you have to prove that the plant delivers the energy that you have put in your energy yield assumptions in your, you know, that's basically you have to prove your promise. Those liquidated damages can range between anything between $200,000 and $4 million per 1% away from passing target. So you don't want to overestimate. You have to be very, very careful. That's again why I said before, you have to be very, very thorough. Of course, test target performance IDs need to be agreed before project is signed. But all this, what does it tell you is that as utility scale projects become fast track, and because there is still a high degree of uncertainty around the rear side gain, because of all the variables that I mentioned before, your risk you have to consider, and that risk is basically going to increase your EPC cost. So on one side you gain because you have your LCOE, which is improving. On the other side, you have to consider the risk that you're facing. And there's a couple of examples. DC wiring, wiring already is quite complicated. It's very, very labor intensive, but you have to capture all wiring challenges before you build your golden row, which is the first tracker row that you build, and then that is basically how all the others are supposed to be made. Why? Because you have to ask yourself where and how long have the module leads to be bifacial modules. Some have the leads in the junction boxes in the center of the modules. Some have it at the edge of the modules. You have to plan everything in advance. Can cable travel across the racking system without shading the rear side of the modules? How will be cable secured? How do you fix a cable? Then cable bending radius, because you put it on a tracker, things move. You have to consider bending radius. There's of course training, quality audit, and quality control measures. So solutions must be fast and cost effective as the module technology, as monofacial. Otherwise, your cost goes up. There's a couple of pictures that I want to show here. For example, you have to understand the home run, the wire harness home run. Where does it go? Can it go like this on the rear side of a module? Or this you have to plan for. There's no room for improvisation. It needs to be validated. The shorter leads, if you have junction boxes, so this is a benefit definitely, but because you have a moving part, then again, that lead needs to get a loop at the post where the posts are to allow for movement because the tracker moves. So all that needs to be very, very carefully planned for, and that is what the impact on DC cabling. But it doesn't end there. The one very tricky part is what we call cable and fuse sizing, because from an engineering point of view, you have to build in a gain safety factor. And that today is open to interpretation for engineers. Why is that? Well, because in the USA, the NEC code 690.7, which is doing the cable and fuse sizing, is for monofacial PV systems only. So for bifacial, you have to take the peak front side, add the peak rear side gain to determine the overall peak current. So you have to know all that in order not to run into a mismatch. And so your increased module efficiency times irradiance gain, safety factor, assumption, etc. Well, because there's no standard industry approach for bifacial current calculations, you have to calculate in that uncertainty, and that can add a cost and quantity of cable, limiting the number of strings you can put in parallel. So because in North America, you use a 32 amp fuse. So all these considerations need to be made, and you have again an area where you may add a cost. And then among these various considerations, fuse sizing, DC terminations, you may have more DC termination to do, increase the DC wire management. Well, don't underestimate the impact of module weight and form factor on installation rates. Glass modules are heavier, are typically 30% heavier compared to a monofacial module with a glass backsheet. When you have hundreds and hundreds of thousands of millions of modules to be installed, what impact does that have on your labor cost and on your installation rates? So DC cabling and module installation cost can again go up. Another part which I think is very important is when you get to the point that you start thinking about doing commissioning and performance testing. You have very important, well, of course, depending on where you are, but in the experience that we did, vegetation variation during commissioning is it's a very tricky thing, because by the time you start building, grass grows, and grass will get as tall as your tracker by the time you're ready for testing and commissioning. So that is a very important thing. Albedo variations, that depends on what time of the year are you going to do your measuring. So again, all these assumptions that you make when you do the engineering of the project then can get immediately impacted by vegetation growing, albedo varying, and it just takes time and cost to manage vegetation, because when you start commissioning and you have to measure everything, you need to get rid of all that grass that has grown after while you were building. So just accelerating a little bit, there's a few more considerations. The impact on a maximum current and IV curve testing. There are, of course, all these standard contractual obligations. Now, in addition to these, you have now challenges when it comes to bifacial. Because, for example, commercial IV curve testers, there's no way that you can measure rear side irradiance gain. So therefore, you only can utilize front irradiation and then trace and translate it to STC values. Then, so our preliminary results so far is that you will end up with preliminary results, and then have to evaluate the standard deviation across traces, compare them with monofacial technology, and make a lot of assumptions. And you have to do this very, very thoroughly in order to get your testing validated. But as you can see, it starts, for example, from something as simple as commercial IV curve testers, right? So then you do your performance testing, and you know that you have to achieve a substantial completion, but because we know that that's the trigger for, you have to match the date. There's a couple of tests that you have to respect, and then both the tests, whether it is IC or ASTM, you have capacity versus measure capacity, and that gives you then the guaranteed capacity ratio. And that is actually what you have promised when you have done the engineering. So you guarantee a capacity ratio between 97 and 98%. You have to do a 5-day test to prove that. but you have to be very careful, because again, you risk into running into liquidated damages between 1 and 4 millions per 1% below guaranteed ratio. You have to be very careful there. And bifacial adds a lot of uncertainty for establishing target capacity and measured capacity values. So there are modifications for the test which are underway, and there's still work from the engineering committees in process, but they're not yet adapted to bifacial modules. So while there is a consensus that bifacial gain should be accounted in for the target capacity values, you need to agree contractually an energy model assumption methodology for generating target capacity with the client. If you don't do that, you shoot yourself in the foot. So bifacial gain assumptions in the energy model, again, they are additional risk for the EPC. Why? Because they rely on these factors that we know are bear high doses of variables. And so in our experience, Albedo is really the large lever for rear side gain assumptions, but on-site measurement prior to testing phase is not typical. So you already have one risk there, and mostly we're using Albedo tables to pre-generate table gains. So we use 3 data sets. We are now proposing modification to existing tests, and that is a suggested modification for bifacial capacity testing by Waters, DeLine, and Weber and Kenitz. So there is work in progress in working on. These are not RES people. These are, I think, from NREL in North America. But there definitely is work in suggesting the way capacity testing is done. So, for example, what we do for capacity testing, we substituted the energy total for the energy on the plane of array. And what typically we do is the energy total we measure is the energy on the front side plane of array. We added the energy on the rear side plane of array, and that is multiplied by the bifacial factor of the module. Now, for the measured capacity, incorporating measurement devices that measure rear side irradiance is important. So what we need to do now is we start adding measuring equipment on the rear side of the test arrays. So it is very important to incorporate these measurement devices because they will basically be the proof of what you're doing. So typically we have 1 to 2 front pyranometers to test the plane of array irradiation, and then 1 on the rear side. That's every 20 or 30 megawatts. So on a 200 megawatt, you have 20 of these, another 10 or 30 pyranometers, and we use the same. They have to match front and rear side device model number, etc. And then you have to make sure where the weather station is, because the meteo station is representative then of the albedo, because that is where you gather all the data. So there's a lot of work on the sensor placement. So the learning curve, which is enormous, is like that you have a limited number of sensors that they must reflect rear side radiance in the majority of the arrays. But then again, met stations, they are typically located closer to inverter cutout areas. And these areas are typically areas where there's a lot of traffic, a lot of trucks going back and forth. You have trenches, so your albedo in that area gets changed. So it may not be representing of the entire project site. And so it can get quite tangled, and on top of that, sensor mounting needs to be considered, shading of placement on the rear side and all that. And I have a couple of pictures here that show where you have to put your temperature sensors because you have to measure that. You have to put your albedometers on the rear side of the torque tube. And all this is new. All this is new because it's just related to bifacial. You don't do all this for a monofacial site. You have to make sure that you have the exact distance from the grade, from the ground. You have to have the right distance from the module. So everything needs to be very accurate and documented. As said, you have to have a very, very thorough and documented approach. And then this is a very good example, is that, look what the ground looks like, because you're near an inverter cutout. There's been a lot of trenching here, so your albedo is not representative. You have to be quite careful for this, and then you all have all the vegetation considerations. So in a conclusion, because I already have run over, and I apologize with the organizers, but in a conclusion, it is not all about the perfect bifacial project design and engineering. Construction and testing uncertainties must be accounted for. That's really very, very important. And I would like to say, and just please, equipment manufacturers, don't take this personally, but a lot of controversy and debate around marginal gains from a module or tracker or inverter in hair splitting optimization should not be the main concern for a developer or an EPC. You can have the most optimized design and engineering, but if you don't have installation best practice, all you do your effort to optimize to the third position after the comma is gone in a second, in a fraction. The IE may take out so many % of your energy yield just because you don't have done your paperwork properly, or you have not documented. You can shoot yourself in the foot because you're wasting too much time in the installation, or you are underestimating DC cabling issues, or you have not been prepared for testing and commissioning. So really, it is a lot has to do with installation best practice, try to get best practice, and all this hair splitting optimization will only make sense if you do know exactly what you do. So far we're here. Sorry it has taken a little bit longer. I hope it was interesting to go through this. If you have any questions, same procedure with our predecessors.
Okay, thank you very much, Tomaso. It is really, really interesting. So that's why, we would like to hear you for, we give you some more time, but unfortunately there is no time for questions. If there are any questions, please use the chat box to answer.
Yes, of course.
Okay, so thank you very much. So it was really, really very interesting.
I'm glad for that.
Okay.